So let me introduce you, Anand Sarwate. He's like a pure electrical engineering person. I don't know when did we have last time as pure electrical engineer like as that. So undergrad in MIT electrical engineering, and then Berkeley Ph.D. electrical engineering, and then UCSD postdoc electrical engineering with the Taylor Technological Institute, assistant professor electrical engineering, and now an assistant professor at Rutgers electrical engineering. And we work together on distributed processing, distributed privacy for sharing biomedical data. And you'll see why Anand is interested and why Anand is involved from his talk, I hope. So please welcome Anand Sarwate.
Hi, thanks for coming. Yeah, so I'm going to talk a bit about some work that I've been doing the last few years, starting from my postdoc, I guess, on privacy-preserving machine learning. So the goal really is to, why do we care about privacy? We care about privacy because we want to be able to share data or access to data to do collaborative research, in particular in the context of medical research. So the motivation really here is this work that I was doing with the IDASH Center, which is a National Center for Biomedical Computing at UC San Diego. And the mission of the IDASH Center is to build tools for enabling data sharing for medical research. So we have a kind of confluence of a couple of trends going on right now. One is the widespread adoption of electronic medical records, partially fueled by, I guess, Obamacare, which has a mandate for adopting electronic medical records, along with advances in assaying and data acquisition technologies. So we have sequencing is getting cheaper. Somebody told me that MRIs are getting cheaper. This did not seem to be the case the last time I had an MRI, but you know, okay. So really, what we're getting is sort of these two things. We have the ability to store and the formatting for storing electronic data about healthcare information, and along with it getting cheaper to get this data. So we have a lot of new challenges in information processing, which you're familiar with here. So the question is really, what can we do with this kind of data? In the context of healthcare, there are a couple of different points. One is just within an institution itself, you could have better automated quality of care tracking, outcomes tracking, comparative effectiveness within a single institution. So a lot of this falls under the notion of decision support. So for a physician, providing them tools to help support differential diagnosis and other things. Another big thing which is motivating my initial investigation of this area was what's called the secondary use of clinical data, which is now you have patient data which has been gathered for the purposes of just regular patient care, and you'd like to then retrospectively look at that information that's been gathered in electronic health records to do research such as comparative effectiveness research. And then the other thing that you might think about more broadly in sort of the work that I've been doing with Sergey is to think about how you would build systems that can do multi-site studies where you have data that's being collected at different sites, and then you'd like to do some collaborative inference from that. So just to dig in a little bit on these last 2 points, the secondary use of clinical data, the way that the systems are kind of set up now is that you have this patient population which has kind of been, you've taken their data and you put it into a record system, and you have a researcher who's going to then ask post queries to the database and then get answers. And so then maybe they can do some exploratory research, so pre-IRB, to check for the feasibility of a certain question. They have a certain hypothesis they'd like to investigate. They want to say, are there enough patients? Is there a cohort within the existing patient population that I can run my study? Will I have enough power for my study? And so the goal is to build systems which support this kind of exploratory research in an automated fashion, as opposed to, say, having to write down a request and have it and send it off to somebody who's working in the IT department, who's then going to then look at that and make sure that there's no problem with it and then send you back a report. But instead, just have kind of an interactive query system. The other point was to look at doing kind of what's sort of called in a lot of places pooled analysis, where you want to essentially be able to perform an inference on data which is held at different sites, like you would as if all the data was in the same site, without actually having to move that data. And why don't you want to move that data? There's the issues of, say, bandwidth. You don't want to, it's a large amount of data at each site, and so it's kind of infeasible to transmit all of the data held at local sites to a central site. But there's also the issue of privacy, of essentially not being able to actually physically share this information because it's illegal. The motivation here is that, of course, with a larger effective sample size, you're going to have higher statistical power, and you'll be able to make stronger claims about it. So privacy is really the main barrier, I think, in a lot of these applications, both from a legal and ethical standpoint. There are some legal protections for so-called de-identified data, and de-identified is governed by laws like HIPAA, the Health Information Privacy and Accountability Act, which says that if you remove certain features, then the data is considered de-identified. We'll see that there are some problems with that. There are a lot of well-publicized cases, in fact, which link so-called de-identified data with public data, and then re-identify individuals. So I'll discuss a couple examples of that, which have been received some press. And the way that these generally work is that you have an anonymized, you have your so-called anonymized or de-identified data table that you maybe publish publicly or shared outside your institution. And then somebody goes along and spends a small amount of money and buys some public record, or maybe just looks up some public record, which is freely available, in which the data isn't de-identified because maybe it's a voter registration list, and so names are actually available there. And you just link these two, and then you end up with a re-identification risk. And the problem is that when you anonymize this data table, you couldn't take into account this other public data that was available, because you also don't know all of the public data that is available. It's sort of not feasible to anonymize with respect to everything. And even for most anonymization strategies that are used now, especially the census-style anonymization strategies, they're susceptible to this kind of attack. So you can mount several kinds of attacks. There's a nice paper by Anand et al. From 2008 that does this. And so the implication here is that sharing raw data, or sharing raw or slightly lightly cooked, if you like, and de-anonymized data is actually, raw data tables is not, it's not really safe. And so the hope would be maybe you can do some other kind of share some access to the data instead of the data itself. So how do things work in practice? So like looking back at this looking at this pre-IRB exploratory analysis workflow, we have a similar kind of problem in that if I am allowed to sort of make unfettered queries to the EMR system, I could potentially reconstruct enough information about a particular patient to identify them. And so, because of that, if you really just want to allow free access for researchers to your clinical data, you would require sort of an IRB approval for that researcher to do that, since it's really hard to write a proposal which would quantify the benefits and risk benefits for that kind of access. So what systems do right now, building a system that's at Partners, for example, is that they limit the kind of questions that you can ask. So for example, they say, we're going to let you have access via a tool which will let you identify cohorts. And so what you can do is just provide, say you want to identify a cohort by demographic features. And it'll let you query ranges of age ranges and other sorts of features to get counts of individuals, how many individuals in the database satisfy those counts. Even if those just unfettered querying with count queries, you can compromise privacy because you can reconstruct enough information about an individual to identify them. So what the existing systems do, such as I2B2 and Stride, there's a system called Stride that's used, which they give approximate answers. So you say, how many patients are there that satisfy these properties? And it'll say, well, around 60. And then you have to sort of say, okay, around 60, I'll do a back-of-the-envelope power calculation and see if that's enough for my study. However, the method of this approximation is a bit ad hoc, and the kind of privacy guarantees are also a bit ad hoc. So the question is, can we make that more formal and quantifiable in terms of what's being protected? And also, they don't really support more informative exploratory analysis beyond count queries. So we want a framework for understanding how you can support the sort of richer data, with visualization, even kind of ways of of playing around with the data in order to get a good sense of whether or not your hypothesis will be true, so that then you can go write your IRB and get the actual data. Similarly, in this distributed setting, how does data sharing work in practice now? In a lot of contexts, you want to do a study, so you contact other people who have data that is related to what you're trying to study, and say, oh, hey, can I get access to your data set? And then the lawyers get involved, and then you have these complicated data use agreements that are sort of individual, institution specific. Maybe I should have colored these different colors for different institutions, but you have to sign a single data use agreement with every person that you're trying to get data from. And so, we thought, oh, well, this might take a few weeks, but then we just had this paper off, and then some reviewer was like, no, it can take a year or more than a year, and it's like ruined his life, I guess. So he's really unhappy about it. So yeah, it's the sort of precludes the overhead, the legal overhead here kind of precludes large-scale sharing of data in an automated fashion. So the key to overcoming both of these kind of challenges is actually develop a risk framework, a privacy risk framework, which is quantifiable, where I can say when I run queries on the data, or when I ask questions about the data, I'm losing a certain amount, and I can compare two different kinds of queries in terms of how much risk I'm incurring for each of these queries. And then what you're trying to do is balance the amount of privacy, which is sort of limiting the amount of access you have to the data, to the utility or the usefulness of the results that you get. And so the way that I'm balancing privacy and utility, I can think of this as sort of balancing some sort of measure of privacy risk versus some kind of approximation error. So if I give you only an approximate answer, how approximate is it? How wrong can it be with respect to the true underlying true count of individuals, for example? And so what I want to ask the question is, for example, how do these two parameters trade off with each other in terms of can I guarantee a certain level of approximation error and a certain level of privacy risk? And the statistical question you would ask is how big a sample size you need to guarantee both of these properties. So these look, I write it here and I think, oh, there's a balance, there's a tension, and in some sense there is and there is not a tension. In the sense that if you have a lot of data, then there is no tension because both of these goals are sort of are complementary. When you're doing a statistical analysis, what you're trying to understand is some structure in the data. You're trying to identify a structure that exists in the data. And if you have a lot of data, you have more evidence for that structure. And therefore, you're going to have more accuracy in identifying the structure. On the other hand, if you have a lot of data, the structure that you're trying to identify is not really a property of individual data points anymore. It's a property of the data distribution, which is what you're learning about. And so you should have less dependence or reliance on individual data points. Outliers should not actually be very important. And so there should be less privacy risk. So we might have a picture like this where you don't have very much data. You have a very small subject pool or a very small data set, in which case you can't really get to your risk error trade-off is pretty poor. You're kind of out here. You have to accept pretty high risk or pretty high error, or both. On the other hand, you could be over here. We have lots of data. Maybe you're Google, and you can get both goals just fine. And the real question is, where are we? Where are you in the trade-off space? And so that boils down to the question of how much data do you need, which is the question sort of asked previously. The statistical question: how much data do I need to guarantee a certain kind of shape of trade-off curve? And then, of course, empirically, you want to know if I try it out on real data, what does it look like? So for the rest of this talk, I'm going to talk about the conceptual framework, the mathematical framework for privacy that we're using, which is called differential privacy. Then I'll talk about how you design algorithms, some applications that we put to work here with MRN, and then a few sort of perspectives on what we need to do in the future. There's a lot of open questions in implementing these kind of ideas. So first on to the conceptual sort of mathematical part of the talk, which is how do you define privacy? And the problem with the word privacy, it's really a sort of linguistic problem, is that it's overloaded, right? There's a lot of, when you say the word privacy, it means a lot of different things to a lot of different people. For the purposes of this talk, privacy is a bit more like confidentiality. You want the fact, like when you go to your doctor, you don't want your doctor to disclose information about your health state to other people. So it's about an identification of you in the population. This is very different than legal definitions of privacy. For example, one famous court case defined the define privacy as the right to be left alone, which is more like to not be surveilled in your house, which is a different notion of privacy than this kind of notion. So it's hard to disentangle sometimes these ideas. So privacy means a lot of different things to a lot of different people. So I want to focus on the agreement, though, between the patient and the hospital, the informed consent decision, right? So when I'm agreeing to let my data be used for research purposes, what am I agreeing to and what is the hospital promising to me? So one point I want to make is that which I'll try to justify a bit better later, is that the data itself is inherently identifying. That is, saying that certain things are identifying variables like your name and your social security number and so on. Those are identifying, but in fact the actual raw data itself is identifying. That is, your gray matter patterns, for example, are kind of uniquely yours and not. And that doesn't have anything to do with your name, but it is makes you a unique snowflake. And so an example of this, which I alluded to earlier, is a famous example from 1997 where LaTanya Sweeney was looking at the fact that this hospital, Mount Auburn Hospital in Cambridge, Massachusetts, would release these discharge records. And a discharge record is used for, is this big table which says some patient, no name or anything, visited, their zip code, birth date, and sex, and when they visited, what the diagnosis was and what procedure was done. This is done for like public health. You want to track how healthcare resources are being used in your community, so it's important data to keep track of. But what she did is spend $20, yes, good, I remember, $20 to buy the voter registration list for the city of Cambridge, which contained these identifiers. In particular, zip code, birth date, and sex were common in these two data sets, and she just did a link and discovered that the governor of Massachusetts had been treated for a certain condition on a certain date at Mount Auburn Hospital. So that caused a bit of a flurry, I guess, of worry and so on. And so then now people are like, okay, maybe we should protect our discharge records a bit more carefully and not publish them publicly, but make people sign use agreements or something to get them. So the point is that the data itself here, if you look at this data itself here, it's these things which may or may not be, you may not think of them as being unique identifiers. They're not saying it's this person, are in fact pretty uniquely identifying. In fact, zip code, birth date, and sex are uniquely identifying for a large fraction of the population, even though they don't contain names. The other point I want to make is that the published outputs of a study allow reinference. That is, anytime I take private data and then I do some computation and publish something about it, somebody could try to use that output to reinfer something about the individual data points. Right? That's what you do in statistics anyway. And so one example of this is the Netflix competition, which is another linkage attack. Who's here has heard of the Netflix competition? Okay, not that many. Okay. So Netflix published, a few years ago, published this data set. They wanted to build a better movie recommendation system. So they published a data set. They said, okay, here's a big table. Person one, no names or anything, that just rented these movies and gave them this many stars. And they gave you a big giant table, and no names or anything, just the set of movies and how many stars they gave them. And they wanted you to build a better system for recommending or rating movies that they haven't seen, so you can recommend movies to them. And there was like $1 million prize if you could improve their prediction accuracy by like 10%. And so what Narayan and Shmanikov did is take this data set and they linked it to people's movie ratings on IMDb and re-identified a Netflix customer, which is in violation of Netflix's own privacy policy, of saying they would not identify their own customers as Netflix customers. And so the point is, the movies that you like, that you have seen and that you have rated and that you like and how well you like them is unique to you. You have unique, you should feel you could be a trendsetter, right? You have unique, personalized taste. That's just you and yours alone. And so even though this data set was anonymized, it still allowed reinference about individuals by linking it to public data. The third point I want to make is that the risk should be guaranteed to individuals. This is really focusing on this informed consent process. When you agree to let your data be used, the researcher should tell you, well, you will be protected regardless of how other people behave. And an example of this is, well, maybe not an example of this, but sort of motivation for thinking about the risks to individuals is the GWAS, the genome-wide association study. And the genome-wide association study, all you publish are frequencies of variations in SNPs across the human genome. So I just say a certain percentage of the population has a G here, another percentage of the population has a C here, in this location of the genome. And what this paper showed is that if I have a sample from a tissue, like a DNA sample from an individual, I can identify whether they're a participant in the GWAS study or not, which is in violation of GWAS's own guarantee to their study participants, that their participation in the study could be kept anonymous. So what this resulted in was now to get the GWAS data, you have to sign an agreement that says you're not going to try and re-identify individuals in the GWAS data, which is, I guess, one way of legally preventing re-identification, but also doesn't really solve the problem. So privacy is lost every time we handle the data. That's the point I want to make. Is that every time I do a computation on the data and publish something, I'm losing something, and I want to know what that something is. And so privacy is really a property of the data processing algorithm itself. It's not a property of the data set. I can't say this data set is private and this data set is not private. What I can say is this way of handling the data is private, or more private than this other way of handling the data. So let's formalize that. So this is what's known as a differential privacy model. And so the setup is as follows. I have a data set D, which has n individual data points. So there are n people in the population compared to the database. And I have some algorithm that I want to run. Some computational procedure that I want to run, which has some output f. And what's going to happen in this setup is that the output f is going to be random. It's going to be random, and that randomness is what's going to protect privacy. So I'm going to introduce noise or some fuzzing of the data in some way in order to protect against using f to reinfer things about individual data points. So the setup is as follows. So what am I worried about? I have I say I'm protecting privacy. I'm protecting privacy against someone who's trying to violate privacy. And I need to figure out how I need to find that. So this other person who wants to violate privacy wants to identify the data point of one of the individuals in the data set. So in particular, you can imagine and he wants to infer some person wants to infer something about this last data point. So I can imagine another database where this person is trying to violate privacy is confused about the values, the data values of this last individual, whether it's xn or xn prime. He's not sure. So under this other possible data distribution, the output of that algorithm will be a different quantity, different random quantity. It'll have a slightly different distribution. And so the point is, from a sample, from a given output, can somebody identify which of these two databases is the correct one, and therefore identify the data, and therefore the identityfulness of one of the individuals. So the definition formally is that the probability of seeing a particular output, that is the probability distribution of this under this scenario, where the one person's data is xn, and the probability distribution under the scenario where this person's data is xn prime. These two distributions should be close. These two probabilities should be close. That's the definition of differential privacy. And how close is dictated by some parameter epsilon, which I'll give you some interpretation for in a minute. But that dictates how close I need them to be. So let's look at the threat model a bit more cartoonishly, I guess. So suppose this last person, this is the nth person in the database. So I'm worried about an adversary who actually, because I'm trying to make a guarantee to every individual in the database, this adversary already knows the n-1 other people's data. Why do they know it? Because they publish it on Facebook or something publicly, right? And I want to make a guarantee. I'm the person running this algorithm. I want to guarantee to this nice lady in the green sweater that she will not be re-identified from the processing that I'm doing. And the adversary gets to see the output because I published this output f. But he's confused. He's not sure if her data is xn or her data is xn prime. So she's trying to do a hypothesis test or an inference between these two alternatives. So she's not sure. Is it xn or xn prime? And the goal of the algorithm is to do a good job on the computation you're trying to do while making this problem difficult. And that's what this definition is guaranteed. It's saying this is difficult. And so How difficult is given by this. So if I look at the false alarm misdetection trade-off, or the type 1 and type 2 errors, if you're more comfortable with that lingo, this parameter epsilon that's in the definition controls the trade-off between false alarm and misdetection, or between type 1 and type 2 errors. And it says you can't have both of them be small. So in particular, you get a trade-off curve that looks like this, and it's saying whatever the errors of this putative adversary are, they lie above this line. So this differential privacy is constraining the trade-off between these two types of error. I can reinterpret this plot by flipping it to get an ROC curve. If I just flip it vertically, I'll get the ROC curve for this adversary. And I'm saying the ROC, the area under the curve, should be close to half. That would mean if it's half, then he's close. And so we can actually plot as a function of the privacy parameter epsilon. I can plot the area under the curve, if you just want a summary, for this particular test. And you can see at privacy parameter epsilon equals 0, that's perfect privacy. The AUC is half. And as I let epsilon get very large, it goes up to 1. So this tells you something, gives you, and of course assessing where you want to live in this, what epsilon you want to use, depends on your risk and cost model for the application that you're using. So why go to this model of differential privacy? Because it has a lot of nice compositional properties that are useful for building systems. And one particular property is that after I publish something that's differentially private about my data, anything that I do afterwards that doesn't depend on the data is fine. It at most can make increased privacy, but it certainly can't be any more risky. So any public processing after my differentially private algorithm maintains the same privacy parameter epsilon, the same privacy risk. So this is the post-processing guarantee. So post-processing doesn't alter the privacy guarantee that I'm making. The second nice property is that if I run multiple computations on the data, which is of course what you're always going to be doing, you're always going to be running multiple computations on the data, then the privacy risk that I incur is just the sum of the two, at worst. Could be even better. There are actually ways of calculating, I mean, there's some ways, we're getting towards ways of calculating more closely, and in some cases it can be much better. But it's certainly, the nice thing is this allows me to budget. So every time you want to run a computation on the data, I can say, okay, you're paying epsilon privacy, and then I can sort of say, okay, you're capped out at this level of epsilon, and then you have to, come back and ask me for permission again. So what this says is, in the context of this collaborative research property, is that actually this epsilon privacy parameter is being guaranteed to each individual data point. So if I have data for different individuals held at different sites, I can separately get summaries or some intermediate computations about these different sites and then aggregate them at a central node, and I'm only incurring epsilon privacy risk to each site. That's the goal. This is to replace the data use agreement model, where I now bound the privacy risk. So the idea is to have local sites share the results of locally differentially private computations, which then they can publish. They can send to a central researcher, a researcher at a central institution here. And this person can then do some further post-processing. It doesn't matter. I'm not going to alter any of the privacy guarantees. And then that person will be able to publish after aggregating to form a global estimate, which is hopefully much more informative than anything you can do locally without any data sharing. And of course, this is going to require enough sites to participate in this process, in the system, because every time what you're doing is you're providing everybody's providing a slightly lousier estimate about their local data. And the hope is you have enough sites to average out the lousiness, the noise from the local sites to improve the overall inference. And so we'll see an example, a surprising example of how well that can work. So, does anybody have any questions about the privacy? By the way, I feel like nobody's asking questions, so now I'm concerned that I've lost everybody. The post-pizza sleepiness has set in. No? Okay. So, I guess I'm going to talk about I've talked a lot about the definition, so now I should talk about how you actually guarantee this definition in algorithms. So here's a picture. It's like a grab bag of different sort of conceptual approaches, right? So I have to somehow introduce randomness into my computation, which is going to, of course, make my computation less accurate. I can introduce this randomness in a lot of, which I can just think of as noise. I can introduce this noise in a lot of different locations. I can add noise to the data and then run my favorite algorithm. That's one approach. This is generally not going to work very well because adding noise to your data is generally a bad idea. I could compute my favorite non-private algorithm and then add noise to the output. I can fuzz up the output of my, which is the same thing. This is similar to what you do when you create a count and then produce and like do rounding or only report ranges, for example. Similar idea there. I could somehow add noise within the process of my computation. That's what we're going to call it. One instance of this is what's called objective perturbation, where I'm minimizing something and I'm going to add noise, so I'm going to change what I'm minimizing. I can do kind of random selection, which is biased towards, so I have like one of k different options, k different values of lambda that I can choose. And I want to pick one of them and I come up with a random selection mechanism. And the selection mechanism is usually referred to as the exponential mechanism. There's also a sample and aggregate, so I could also subsample my data and then do some kind of merging operation, and that's kind of like bootstrapping in statistics. So all of these are kind of generic approaches depending on what your target goal algorithm is, what your goal, the computational goal you're trying to achieve. One of these may be better than the other. And so let's look at this in a very simple case, just so that we get a handle on what's going on. Suppose I want to compute the average. Suppose these are the salaries of n individuals, and I want to compute the average salary. If I compute the actual average salary and publish the output, an adversary who knows n minus 1 of the salaries because they've been published on Facebook can infer the last salary value very easily. That is to say, this output is a deterministic function of the input, so it's easy to say that that you can reinfer one value from the others, knowing the others. So that's bad. So that's the picture. An adversary observing the output and knowing n minus 1 salaries knows exactly what the salary of this last person is. I work for a state institution, so all our salaries are public anyway, so I guess this is not a concern for me. But, you know, maybe at other places it's different. So what's the solution? The solution is suggested by the first paper on differential privacy is, well, why don't I just add noise to the average? So I'll just report a noisy version of the average. So I'll add some randomness to the actual average, and now this output has a distribution. And the noise you should choose, well, they choose a Laplace distribution, which is kind of looks like this. And I just add that to the value to the true average, and it turns out that that guarantee churned through the definition of differential privacy that guarantees the differential privacy guarantee, and the approximation error has variance that scales like 1 over n epsilon squared. But the standard deviation scales like 1 over n epsilon. So for a fixed privacy risk epsilon, as I have a larger and larger data set n, the error variance is going to 0. So that's what you want. In the large data setting, you end up adding very negligible noise and still guarantee privacy. But this epsilon constrains how much variance you need to add. So as I said, the error variance goes to 0 as n increases, and this is even though the adversary gets n minus 1 data points. That's because the actual average is not really a function of any individual data point when you have a large number of data points. So it's easy to guarantee privacy. That's it. Okay. So this raises the question. How should we randomize our algorithms to get the trade-off between privacy and error in this setting where I have a generic thing that's not just the average. The average is nice because I can break down things. And so if I want to choose how to randomize, then I should really understand a bit more deeply what's going on in this average example. So let's consider this case where you have multiple sites. And all I want to do is say, get the average, suppose I want the average activity region in some, average activity level in some set of voxels in the brain somewhere from different sites. So I average over subjects in each site. So each site could take a local average of their data, of the activity, and then add their own noise. And then I know that the error variance, I can compute the error variance of their own local estimate. Their own local estimate but in this case, is going to have error variance that scales kind of like 1 over n and 1 over epsilon n squared. But now, I have many sites, right? And I'm the central researcher, and I'm getting these noisy estimates, from which are down differentially private, from all these different sites, and now I'll just average all of those. So this is the larger sample size advantage that I'm getting from sharing results of computations. If I do that, then I get a reduction in the error variance by the total error of my estimate by another factor, 1 over n, capital N. Capital N is the number of sites. So the question is data sharing helping? When I want to ask, is data sharing helping? The answer is, well, is this number significantly better than this number? And so you benefit when the number of sites that you have is bigger than, more than 1, obviously, but 1 plus epsilon squared over n. So this tells you, what this does is tells you for a given privacy risk epsilon and the amount of data at each site, how many sites do I need to participate in order for this to be worthwhile? And this lets you do study planning better. The goal is to build estimates like this. Okay, but this is just an average. And an average is like only one very simple statistic. So let's look at a more difficult task, which is classification. So in the classification task, I have a researcher wants to learn some way of deciding, some way of determining, given a patient, whether or not they're high risk or say low risk for some condition. So mathematically, the data of each patient is labeled X, is X, and there's a label Y, which is +1 or -1, depending on their high risk or low risk. In this case, it's pretty clear that hats are low risk. So you should wear hats to avoid maybe skin cancer. This guy might be in trouble. So the goal is to produce, in this model, is to produce a linear classifier, in this case F. So it's another vector, and I want to look at sort of this F determines this boundary region. It's time to decide. So a popular way of doing this, and this is, I guess, the most math that's going to happen, is to pick the minimizer of some of this function. And this function is the sum of two terms. It's the sum of the empirical risk, that is, how good is F on my existing data set summed over my data points. And then this regularization term, which is to prevent, so-called to prevent overfitting. This is actually a lie. It's controlling the norm. It's not directly preventing overfitting. But that's what we say when we're telling ourselves stories. And so you can do this, and so how do you minimize this? You can do this using a standard gradient descent or some sort of stochastic gradient descent. So lots of algorithms, there's toolboxes out there to do that. So minimizing this is not hard. But the question is, okay, well, this doesn't look like it's very much a function of the data. So is it actually differentially private? And the answer is no. If I change one data point, then the best F is also going to change. So it's the same as the average in the sense that I have to protect against all the data, all of the data points. So this leads to, so you can think of two different ways of maybe guaranteeing differential privacy in this setting. One is I have lots of software tools already to do this minimization, so maybe I should just use those. So I'll use those off the shelf, and then I'll add some noise afterwards. So I'll compute the best decision boundary, and I'll kind of shift it a little bit. And hopefully, if I've learned a good one, then shifting a little bit shouldn't incur too much additional error. The other option is not to reinvent the wheel, essentially, and change what I'm minimizing. That is, add noise to the thing that I'm minimizing. And then now what I'm essentially doing is I'm saying, well, normally I'd want to find the best classifier according to this criterion. And I'm saying, let me change the criterion a little bit randomly. And that changing my target was actually going to be enough to guarantee privacy. It turns out you can prove that both of these algorithms, if you choose the noise distribution appropriately, are differentially private. So I'm a theoretician by training, so my goal is essentially to analyze the trade-offs, theoretically, to analyze the performance of these two algorithms. So I can achieve a privacy risk, an additional excess error, so epsilon and delta. This method requires 1 over epsilon 3 to the halves delta. This one requires 1 over epsilon delta. So I say, okay, this one wins. But what do I mean by winning? So if I want a very small privacy risk, then it would suggest that I need 10 times as much data to run this algorithm, which is like 10 times the cost. So it can be quite significant, but then again, this is all just the theory analysis. So the question is, does this actually obtain in practice? And so 10 times as much data is a little bit more than I would want to say about the practical results that we have, but it is true that this method is significantly worse than this method on real data. So what are the implications of sort of the theoretical analysis and algorithm design? So actually, maybe in the interest of time, well, I'll sort of skip these first 2 points because I think it's a little bit too nitty-gritty. I'm happy to talk about it offline. But there are actually a lot of other algorithms out there that have been proposed that have not been tested on data. So there's a lot of work actually to be done to see how well these algorithms work in practice in addition to the theoretical guarantees. And so what I want to turn to now is actually looking at what happens to can we make differentially private algorithms that sort of work with existing systems or with existing data sets. So this work is basically the first and the last paper. The last paper is obviously one of the books here. This first paper is some very preliminary work we did in the context of this cohort identification problem. So let's go back to the cohort identification problem. I'm a researcher at UC San Diego. There is a clinical data warehouse at UC San Diego which has about 2 million patient records in it, or 2 million patient visit events in it. And I want to understand, I want to find a cohort of patients to use, say, in a retrospective study to compare the effectiveness of, say, warfarin versus Coumadin, which I guess are 2 different blood thinners. And so I need to find all the patients who have those, who are taking those drugs, for example. So what I do in practice is I issue, there's a web tool, you log in, and then you issue queries to the database where you specify, narrow down the cohort specification so that you can, to see how many patients you have so that you can, that you could potentially enroll in your study. So how that works, so, okay, queries and answers is big, so maybe I might start, maybe my study is on diabetes and hypertension. So I first ask for how many men are there between the ages of 30 and 40 in the whole patient population. And maybe there are 3,345. Then I say, okay, great, that's a lot. I'm not just interested in that. I want to know also, do they have diabetes? Okay, so I add plus diabetes to my search. And then it says, okay, only 829. That's actually a lot out of the 3,000. So this is unrealistic numbers. Sorry. And then I say, okay, what about, what if I added hypertension? And then I say, okay, now there's 314. So now I'm kind of happy. And I say 314 is a lot. Probably most of them are not going to fit the other things that I want for my study criteria, but at least I know that there's a large population to do my study. And what happens in existing systems is that they provide approximate answers like this, but they don't actually measure anything about the privacy risk of how you're querying. And furthermore, they don't let you do things like tune how much. So because I can choose epsilon per query and get more accurate answers later on when I'm getting smaller numbers. And overall, my privacy risk will still be bounded. So that's a benefit of a system that we want to build. The restrictions that exist now on systems like Stride are essentially if you ask the same question. So Stride, these systems add noise, and if you ask the same question 6 times, it boots you off. So like you can't average out the noise too much. That's the right. And that's kind of not. I mean, that's a security precaution, but it's not doing it at all. So the standard differential private solution is just to add noise to counts, which is what the existing systems do. So what I'm going to actually do is release the true count plus noise, and I'm going to choose my privacy parameter epsilon. This is the question I always get asked: how do you choose epsilon? Well, in this case, you choose epsilon to match whatever the existing system that's being used that people are happy with that matches the noise variance of the noise they're already adding. Then people will be like, I'm adding the same amount of noise. So it's the same kind of system you have, only now I'm doing better tracking of how you're using the system. And I'm going to give you some more flexibility by letting you choose the amount of noise interactively. And in addition to this interactive choosing of epsilon, we can provide additional features to tune the noise distribution to account for biases in terms of over and underestimation. You may be very worried about overestimating the number of patients, or you may be more worried about underestimating. And by letting you do this, you can get more accurate answers over a sequence of queries than you would be able to just under a standard one-child model that exists now. So this is so the benefits of this are essentially we now give the researcher who's doing this exploratory analysis a privacy budget. We say you're allowed to spend this much epsilon. Go ahead and ask your queries in whatever order you want until that's your sort of pre-study privacy budget. And the budgets can be tuned to depending on how much you trust that researcher in your organization. So this is sort of compatible with the role-based access that we already have in some of these systems. Furthermore, this privacy currency, because I'm using this epsilon, I can extend this to beyond just counts of patients, right? I can allow people to, say, compute a classifier on the existing data to see what kind of whether or not there is a strong signal for some variable being able to tell me something between high risk and low risk. So this is actually being integrated into the UCSD clinical data warehouse through a tool called Cricket, which is an acronym that I can't remember exactly what it stands for. Clinical Records Ticket. And the goal is essentially to expand what we have right now with these count queries. The goal is to kind of expand it into other statistical tasks, build a kind of pre-exploratory, pre-IRB study tool. I think there's a lot of open questions here in terms of data visualization to help researchers. And this is the kind of question that I would want to know is sort of what kind of, if you are running this kind of pre-IRB study, what sort of questions do you want to be able to answer prior to being able to get the data? What sort of functionality do you think important? What statistical tools would be useful to you? Summaries or tables or indigency tables and so on. Because that's really the key to making this sort of practical. So just in the last few minutes, I want to go back to the problem, the whole reason that I'm here, which is this paper that we just published in Frontiers. So here, Sergey knows more about the data set than I do. So it's a merged data set on schizophrenia from, well, I'm sure everybody here is familiar with this data set. So we have structural MRI images for about 389 patients. Pretty balanced, actually. This is surprising. I mean, it's so balanced. And so the goal is to build a classifier to distinguish patients with schizophrenia from healthy patients using the structural MRI. And the cheating that we're doing is we're reducing this 60,000 voxels down to a 50-dimensional representation, and we're learning these features without any privacy guarantee. So we've already picked out some good features. But even without picking it, so the goal here is really to understand how does this local privacy affect the quality of inference that you can do at a central site. And so the goal is, the real goal is to say, if I only had data at one site, how well could I do versus sharing data, getting data, getting some differentially private summaries from other sites. So the insight here, algorithmic insight, is that because every site has a small number of data points, each site is not going to be able to learn very much that's useful about the data. It's not going to actually learn a very good classifier. But it does learn about some salient feature of the data. So it learns about some direction in the data that is important to the task of discriminating between healthy and patients, the patients with the condition, patients with healthy. So for each site, what we do is we train a classifier using this differentially private ERM. So that tells me about one direction in the data which is useful. And then I treat for a new data point, I treat this as giving me a new feature that's relevant for the classification task. So now if I have n sites, the central aggregator now has n different features from n different sites and has their own data set. And they use that to compute new features. So it's computing a new representation of the data locally based on these what I'm learning from these other sites. So this is the method. Let's just put a picture. So here's the picture. So every local site is learning n different sites is learning from a local data set in a differentially private way using support vector machine, learning one direction of the data that's relevant. The aggregator has its own data and uses these to retransform its local data into a new representation, and then trains this is a private aggregator. And trains a new classifier based on that and publishes that. All of this feature representations, these can all be published publicly as part of the system. So how does it work? So here's the stunning experiment. Thank you to everyone for running the experiment. 10 sites with private data. Each of them has a baseline accuracy of around 22%. So error of 22%. So that's pretty lousy. But this aggregator who gets to treat each of the things, and the aggregator itself also has about 22%. So the aggregator, who uses the information provided by these local sites, not in terms of not as the classifier itself, but as telling you something about the data, can bring the overall classification error down to about 5%. Of course, with error bars. This was actually very surprising to me, so I'm very happy. I forget what epsilon was at this experiment. 1 though, right? Epsilon's like 1. How about data?
1. Epsilon was high actually.
Epsilon's high.
Maybe 2 or 3.
2 or 3. So, but this is so in my view, you really need to pick epsilon based on what's going to give you good results. You worry about the quantification. You care about the quantification part more than the actual absolute value part. So what are the implications here? I think this is a good pilot study, which says that sort of the distributed approach to learning local private features and then communicating them to a central site, where I'm only really computing a derivative of the data, not actually communicating the data itself, can be feasible even when the sample size is small in each site. And that in the presence of this privacy constraint, the algorithm, the way that you would design an algorithm for this aggregator is going to be different than the way you would design it, say, without privacy. Without privacy, you would do something different. And I would say that there is lots of work to be done, in general, in this, designing new methods and then trying them out in differentially learning. So just the last 2 minutes. I hope that I have convinced you, maybe I haven't convinced you, but I hope I have, that differential privacy is a kind of promising framework, at least, for thinking about these problems in distributed data analysis. As I said before, there's like tons of algorithms. Most of these are like in the CS theory literature and not with no experiments. And so the hope would be to do more empirical work and see which algorithm choices, which look good on paper, would really look good on practice. Sometimes yes, sometimes no. The guarantees, because the guarantees they often make are very asymptotic, and in particular in the case in neuroimaging, we don't usually have very large subject pools. So there's more work that needs to be done to be clever about your inference method or algorithm design to take advantage of things that you know about the data. In particular, things like the high dimensionality of the data can often be challenging. The reason that we got such nice results is because we had done this pre-dimension reduction step to 50 dimensions. And there's a real need to exploit domain-specific properties or to build adaptive methods that kind of learn something structurally about the data that you can exploit then in the algorithmic phase. And this is kind of an open question how you do that. I mean, adaptivity in statistics is also an interesting open problem. So as a summary, I think there are lots of interesting algorithmic and statistical challenges. Differential privacy, I think, is I'm not an evangelist, so I don't want to be like this is the only way to think about this problem. But I think that it is a useful way of thinking about this problem, and has a lot of nice properties that work well with system designs. So there are a lot of strategies for designing algorithms. These algorithms are useful, I think. We've shown at least empirically once. And I think in terms of biomedical research, we have a lot of interesting domain-specific challenges. And I'd be very interested to know sort of what kind of statistical tasks are relevant in the kind of research that you do that would help inform sort of what choices of what new problems to investigate, what kind of functionalities we should focus on implementing. So thanks.